let's pick up where we left off before our demo day on Thursday. And it was starting to get a little mathy, but I don't think nothing we couldn't handle. But just to bring up, kind of one of the final equations to talk about lighting calculations, and it looked something like this. One takeaway from this that I think is sufficient for understanding how we do lighting for modern, kind of rasterization, real-time rendering systems is that there's just three components of the lighting. There's the diffuse lighting, how the light source interacts with the plane of the object that we're rendering. There's then the so-called specular highlights, and you'll recognize that via that alpha term. There's an exponentiation term going on there where you get to set that as an additional parameter. How shiny, how tight do you want that shiny region to look like for that particular object? Both of those terms have a characteristic of the light source. Those are the capital I vectors in this slide, as well as the material properties. Those are the lowercase k here. And that separately would have its R, G, and B components. So there's a lot of vectors we're specifying. Oftentimes, k will be something that's dictated per object. I could be per scene. It could also be separate per shader as well. And then you're multiplying those components together with both the diffuse calculation, where we're doing a dot product to kind of give us the cosine term here, and the specular highlights to kind of show the very rapid decreasing of the specular highlights. And then for all other lighting source, which may or may not be meant to be kind of physically accurate, but all of this is an approximation on top of an approximation anyway, we have this ambient, this kind of background lighting, which is all other lighting calculations taken into account. We don't want objects necessarily to not appear if they don't have any kind of interaction with those manually specified light sources. We have this background lighting that makes sure that everything has some kind of minimal amount of lighting here. If you know this equation and generally have a high level understanding of it, that's probably sufficient. Today we'll talk more about what does that mean in practice to implement it. The other point that we brought up relatively quickly, and I don't think it's that important just to recognize though that what is done in modern practice is when doing this specular highlight for kind of the original Fong papers and how he kind of derived this concept, using V.R for the specular highlights. This is the perfect reflection of the lighting source. This is kind of the I vector or viewing vector. This is back to where the camera in the scene is. The recognition that at least when doing it on a fragment by fragment basis, that calculating this R was kind of a lot of extra work that potentially had to get done here. V we kind of have to do anyway when we're doing our viewing. We have to take our coordinates of our vertices, our objects. We have to translate them into world space via that model view matrix calculation we're already having to do. But R is something we don't otherwise have to do. And so it was recognized that you can use this so-called halfway vector that is more efficient, at least when it's being done at the fragment shading time. The more I think about this kind of phrasing that I used here about being more efficient for the modified Fong or for the blend Fong rendering equation, it's really only more efficient if it's done at fragment shading time. At vertex shading time, you have to do all these vector calculations anyway, and so it's not really that clear to me that it's more efficient at that time. But this is what we tend to do in practice. Instead of doing V.R, we do N.H, where N is already something we had to be provided, so we have to have it anyway. H is something we can calculate at vertex shading time, where we're looking at effectively that halfway vector. There is no physical interpretation of this that at least I am capable of giving you that I think is convincing of why we can do this versus doing V.R. Why we can choose this angle effectively is what we're doing with our dot product versus this angle. I think a reasonable understanding to take away from this is that in practice, for lighting objects, they tend to be very relatively close to each other, at least the right order of magnitude compared to each other. So it is, again, it was already approximation on top of an approximation. Now I would call that a hack on top of an approximation on top of an approximation, but in the good sense of the word, that you get a reasonably close value. It's not identical, so you can get your objects to look reasonably shiny with those highlights by doing this calculation instead, N.H versus R.V, and consequently changing that alpha term with a beta term. So for the power, the exponentiation we're doing, you may have determined for this particular material, alpha equals 20 was the value you wanted, and then you change this, the angle is actually potentially going to shrink, you change it to a value of For a smaller angle between them, you want to change it potentially to a larger value of beta to get the same result. But that's all you have to wind up doing. And that's the main advantage. We don't really see that advantage in the vertex shader, but if you're doing it in the fragment shader, you would see potentially that advantage. This was the final demo from all the way back a week ago Tuesday when we were doing this. This was using kind of the old school way of specifying light sources manually. I also want to talk about how do we do this in practice, where we don't have dedicated functions for the specific parameters of the Blin-Fong model. So this will be a very similar looking demo here, but the code it's running is quite a bit different. So I won't bring up the prior one, although we have it here. This is another spinning, shiny, specularly highlighted torus. And we use tori for the same reason we use spheres when doing these kind of demos, because similar to our sphere, the normals are something that we can just calculate. We don't have to specify them. You can think of it as a sphere has a normals kind of going out from the origin. There's similar properties of a torus. If it was any arbitrary shape, then we can no longer do that. And when specifying the object, we would also have to specify for every vertex, potentially for every texture coordinate. We would also have to specify every normal as well for each of these vertices. When we loaded up the seal model, that's what we had in that model. That's what Blender was exporting, not just vertices, but also the normals. You either have to provide them or you have to calculate them, unless you have some mathematically defined object, and then you can mathematically derive what those normals should be as well. If we take a look at what that is in practice, the only downside of this coding example, I have slides for it as well, is it does the shader kind of inline, which you're allowed to do. You're specifying the shader is just a series of strings here. We can kind of squint and look at this and get kind of a feel for what it's doing. First off, that object was spinning, and we can talk about how it's doing the spinning, which is being shown right here. The actual rendering of the object is locked behind a little loader helper library that's loading a binary blob specifying the torus. But our actual displaying of the torus in the scene takes some random time value that there's just a tick counter that's incrementing as we're running the application. And it's using that time parameter to determine rotation around the x-axis and around the z-axis in kind of an arbitrary amount. So it's just spinning the object, and it's doing so not using the GLM library, but using something extremely similar, VMath library, to allow you to do the translate, rotation, and to calculate those matrices according to it. So when we talk about viewing and what that looks like in modern programmable shaders, it's usually going to look something like this, where your user code, your C code, your CPU host code is doing some of the initial kind of matrix setup math, because we may want to be spinning the objects. We may need to calculate this once per frame. The end result is we're passing one or two or multiple matrices to the shader. The shader is then actually doing the matrix vector multiplication along the way. Now what this example is doing in addition to it is we have some additional uniforms associated with those parameters for ambient, diffuse, and specular. That would be our K values from our equation. And our actual shader, we'll look at this example, and then we'll look at a slightly different example that I think would be a little bit easier to read. Model view matrix, projection matrix is our uniforms. Our inputs are the vertex position and the vertex normal. Our output is our viewing transformation vertex, as well as our normal. Our position, we do our model view projection transformation. So that's a matrix followed by a matrix vector multiplication going on here, right? Modeling matrix, calculate it times the projection matrix, take that whole resulting matrix, that is our viewing transformation. We did not, when we covered this topic, we kind of skimmed over when you're doing orthographic or perspective views, what that matrix winds up looking like and how you're able to get the various stretching and scaling. But the end result is you do wind up with a matrix, and calling these kind of functions generally is a lot easier to do than to try to derive those 16 parameters by hand. So those slides are there. We really kind of skimmed over them, but ultimately we're providing those matrices and we're doing that calculation here. Now there's a little bit that's happening here, and we got to think about it kind of briefly. Here, and I mentioned this may sometimes be the case, Other examples had a single matrix we called a model view projection matrix. Whereas in this example, we separate them again. We have a model view, it's just calling it a model matrix here. We have a separate projection matrix, and we treat those as two separate entities. The resulting math for our viewing transformation is still the same. Combine the two matrices and then do the multiplication, either in the shader or do it in your host application. The reason we separate it out, now you can see for this lighting example, and I mentioned it, but now you can see it in practice, that for determining where our vertex should be, we have to take the camera into account and what kind of perspective we're viewing the scene in. All of those components get multiplied together to get our final XYZ location of our vertex. But we have a sphere, or we have that torus, and we're moving that torus around in the scene. We're rotating it, we're translating it over here, we're doing those modeling and viewing things. We need to apply that same exact transformation to the normal that we specified as well. But the projection matrix, where we're determining what kind of angle we're viewing things at, that does, at least from like a physically real-based rendering perspective, doesn't change where our normals would be. It wouldn't move our normals, it wouldn't stretch or rotate our normals. So we don't multiply our normals by the projection matrix. We only multiply them by the modeling matrix. And that's why when you're doing lighting calculations, you tend to see those two matrices separated here. I don't know how visible that is, but that's what's happening here. So in this case, and the example I'm going to show in just a minute is doing it slightly differently, we're not doing lighting calculations by and large in the shader. Shader's not exactly a pass-through. It's doing the viewing transformation, and it's passing along our normals also translated here, and then our lighting calculation is happening here in our fragment shader, where we do have the uniform specified. Otherwise, there's some default values. Well, first, let's start to begin with. We got to specify a color for our fragments as they come in. We have as inputs some direct relationship between the outputs of our vertex shader should become the inputs to our fragment shader. This is done via named attributes. In other versions of OpenGL, and it really is very version dependent, you would do it based on positional attributes versus named attributes. But in this example, the version of OpenGL has the names being the same here.
Is that newer versions?
This is 4.3. Well, no, in newer versions, there's more than one way to do it, unfortunately. So the version we are doing is also using this keyword. Our compiler, our own compiler for the lab infrastructure, finds this kind of problem to be a little challenging of how do I make sure that this corresponds to the same thing as this? So we require that you specify the location being the same. So and it also, of course, our hardware also has other requirements that color is always location 0, and you'd have to change a lot of your hardware code if color wasn't location 0, right? We have our KA, KD, KS, as well as now whether you want to call it alpha or beta parameter here. We also, in this case, have the lighting position, which I think when we were doing the application, it can be sometimes hard to tell. Is the object moving, or is the lighting moving, or both? I think if we were to look at this example here, what do we think? It'd be a lot easier if I paused it. What do we think? Obviously, the object's moving, so the torus is moving. Is the lighting also moving? By the way, part of the reason this looks kind of like laggy, again, we're remote desktoping through a VNC connection. This should run reasonably well. This is a nice piece of hardware it's running on. Let's look for light position. Well, that's only going to be in the C code in one place here, where we would specify by name the uniform location. In this example, does not. So the lighting is fixed. It's hard to tell looking at it again, right? Because where I would look for is the specular highlights, and are they kind of moving here? I guess if we really want to, first off, I'm not sure if I can build this example. Let's make sure I have everything set up to. Now you have to make them all, which is fine for this whole set of example. Using CMake. Assume I have this working. Hold on. Yeah, you have to make all of them, which is kind of annoying, but fine. Let's just turn off the rotation. There's a lot of ways we could turn off the rotation of the object. There's the right way, the wrong way. There's my way. There we go. So time does not change. That should work. Assuming 0.0 leads to, let's assume app time is just some like tick ANDed with that. So take the lower, I don't know, what is that, 16 bits of it, and then divide by the possible. So it's a fractional value. So 0.0 should be something. It's not like it's going to disappear if I run this with 0.0. There we go. So I mean, it's fine. It's not rotating, but it's not supposed to. It's just kind of staring at us, and our light's not moving either. So we could change that as well. Right? We could write this code now that I think we know enough about OpenGL. If we wanted to instead pass that time parameter to the uniform each step, and instead of moving the object, we could be moving where the light source is. But it just so happens, and I'm going to go back and change that back because I'm going to forget. It just so happens for this example, we're moving the object, but not the light source as well. Semicolon. That's my advanced Linux command there. To limit the amount of typing here. Okay. So light position here is a uniform. You can change it, but it's just given a constant position here. Let's try to walk through what's happening here. Let me do the example that's on the slide. I think it'll just be with a little bit of syntax highlighting. You can see it a little bit better. So it's doing something extremely similar here, but this example I made so that it was kind of more just easier to read on a slide here. So this is lighting in the vertex shader. It'll look subtly different. We'll talk about some of the difference here. But in the vertex shader, I think the first thing you'll notice is that once you have lighting as part of your render that you're interested in, there's a lot of other of these like vector quantities that have to be used in the lighting computation itself. So of course, position is always there. If we're doing lighting in the vertex shader, color is going to be one of our required outputs. And then we're always having to specify these normals because that equation, both of those take those normals into account. We also have to then have our K values, which would be easier if they were called KA, KD, KS, but that's what this is going on here. We also then would have to have, like in the other example, the position of the light, and then that alpha or beta component for what power we're raising our specular highlights to. Like in the other example I was showing, here for the same exact reason, you do have the two separate matrices. So you always, I think, would have those in your host code. Now you're just passing them separately versus doing the multiplication. So you can do that initial transformation of the model view. That's the first part. Translating wherever our vertex is in model coordinates into our camera coordinates or our world coordinates here with our model view transformation here. We then have to determine, where is our light source relative to our object. So let me go just quickly back. I'm not going to belabor it too much. We have to calculate this. Now we specify this. So you may be wondering, I specify light position. Why do I have to calculate this? Really there's two reasons, right? We specify where our light is, but then we're also moving things around in our scene by applying that model view transformation. So while we do specify our location and we specify this, the very first thing we do is determine that we're moving things around. So we have to determine now, after we've moved our object around, where is our light source relative to that object? That's the one thing we have to do. The other thing we have to do, although I didn't exactly mention it, it was in the slides here, is for that dot product to give us basically that cosine value for the angle between them. Both of those vectors have to be normalized. You can either find a way to guarantee that it's always normalized via just some specification tricks, or if you can't really guarantee that, you're going to see a lot of these calls to normalize either people doing it manually or just calling the built-in function normalize to take that vector and divide it by the length of that vector here. So where is our light relative to our position? That's the difference between them. We then normalize that result. That's the first component we need to have. There's also that vector which was called V in this model, and in this slide it just happens to be called E. That is from the point to the camera. We actually technically have that, and it shouldn't make that big of a difference, but we're pointing back towards the camera here in this point. Then we have that halfway vector, H, which is the halfway between V and our L in this slide here. It's called E, but it's the same exact calculation here. So L plus V divided by the length of it, that's L plus V, then normalized here. You oftentimes just see L minus E, but it's the same exact calculation that's going on here. We then have to move our normals around as well. We've specified them, but then we've moved the object. We have to move the normals correspondingly as well. We do our diffuse calculation here. So here, the expressiveness of GLSL makes life relatively straightforward in terms of the amount of lines of code that we are writing here. We're calculating the dot product. There is an extra small little wrinkle that if the dot product winds up being negative, there shouldn't be any lighting correspondence to it. So the light's coming down, but the object's actually facing the entirely opposite direction. That'll lead to an angle being greater than pi. That'll lead to the dot product being negative. We are then checking for that. You don't need to really use if statements for that in this case. We take the maximum of the result of the dot product with 0.0. So we're whatever we're going to call it, truncating it or limiting it to being a positive or zero value here. And we calculate that diffuse product. We then do the same kind of calculation we talked about for the specular highlights, where it's n.h for the Flynn version versus v.r. For the same reason, we check to see if the actual dot product is positive, and we're actually raising that value to that exponent. So n.h to the beta to get our specular contribution here. You may note that the use of KSKD is a little different than in the equation, but it's doing the same calculation here. So there's the property of the object itself, the material properties. How much should this object care about ambient lighting, diffuse, specular? We talked about, right, why is a certain object green? Well, because it reflects certain spectra of the visible light and then absorbs others. And the end result of what gets reflected back to us is looking green to us. That's what we're attempting to specify via these vectors. Otherwise, if you have white light and you're equally reflecting all contributions, all of your objects are going to look white or variances of gray in your scene. So there's our diffuse, there's our specular. There's a check here that if in fact we had no diffuse contribution, there shouldn't be any specular contribution. I've seen versions that don't do this at all, but that's, I guess, a way of checking that. If the light source, again, is here, and we're not at all facing the light source, that even if somehow mathematically you wind up with the result here that leads to some specular highlight, we shouldn't have any specular highlight. There shouldn't be any contribution from the light source here. And then our final color contribution is just those three terms just added together: ambient, diffuse, and specular. And that's effectively what's going on here. Now, separately, we had to then, we previously had calculated our position value, model view times position. We do have to get the final MVP transform back out, which winds up happening here. We could have also just done projection times position. That would have given us a good result as well. For doing these kind of calculations, we don't care about that fourth coordinate, but for this one, we do care about it, so we do it separately with our 4x4 arithmetic going on here. And there's variants of this. There's different ways of specifying basically the same exact thing, but when you're looking at lighting, either in your vertex or your fragment shader, you are going to get some version of effectively this. And those of you who are interested in looking into lighting, what is going to be new for you? There's going to be normalize. That would be new that you'd have to be able to implement. Normalization requires division. I guess it depends on what the shader compiler emits for this. But either way, if you've already had to add a divider to your IP core, somebody got a divider working already. Was that your group, or at least in the shader you got it working, in the host side shader. If you already have one divider you've added, just reuse it for this instruction as well. Should be doable, but yeah, you have to make sure you can get the division working. So it's an addition plus a division. The dot product you should be able to support already, depending on whether you implemented it already or not. That's just multiplication and addition here. Max should also be something you should be able. I mean, I keep saying you should be able to support. Each one of these requires testing and debugging and making sure you understand what's happening here. I would argue that when you get to the point of a project, trying to solve all the edge cases maybe isn't your primary goal anymore. Working backwards from what you'd like to be able to demo is probably going to be sufficient for all of these projects. The one that would otherwise kind of complicated would be the exponent or the POW operation. I guess I would say save that for last, right? The main influence of having a POW operation is you get like a tighter and tighter highlight here. Well, if you assume shininess is equal to 1.0 and you test with that, then you don't need that operation, right? Or if you assume it's 1.0, 2.0, or 3.0, or some integer value, well, you can implement that as well, right? That's just a little state machine that keeps doing multiplication n number of times. All those things, should be okay. Whereas trying to implement an arbitrary floating point exponentiation operator, it's at least a lot of hardware resources, if not a lot of time to implement. So maybe you don't need that, right? In terms of what you're trying to demo at the end of the day. So, think about that, and it's something that I think is very doable for your vertex lighting calculations here. And let's talk about that. The two examples were kind of subtly different. Although if we were to, I don't know how easy I can bring them side by side. If we were to look at the actual lines of code doing the calculation here, all the variables were named something slightly differently. But it's exactly if you look at it, it's exactly the same in terms of the math involved here. There's the light calculation for the vector L. There's the normal, which here we normalize it in the fragment shader. There's the half vector calculation. There's then the dot product for the diffuse, the power to the dot product of the specular, and then the color all getting just added together. So it looks a little different in a slightly different perspective on the same implementation, but mathematically it's doing the same exact thing for this example. But there is a difference in terms of where we are doing our shading and what the end result would look like. There's really three main types, whereas this is talking about kind of two main types. And the three you want to think about, they're generally referred to as flat shading, Gerard shading, or proper Phong shading. Because when we do things on a polygon by polygon basis or on a vertex by vertex basis, the end result is you tend to see the results of interpolation of rasterization more clearly here. So we talk about normal and what a normal is mathematically, right? A normal is a property of a plane, or in our case, a property of a single polygon. You have 3 points, you calculate the cross product, you get a single normal back out. So at least conceptually, one could have a version of a shader in which every vertex for a triangle is specified with the same exact normal, because mathematically that's kind of correct. You have the normal is a property of a plane, not a property of a vertex. That is what tends to lead to a very flat looking result. That's so-called flat shading here. The example we did with the sphere was effectively flat shading because we specified basically the same normal for each of the vertices associated with the quads we were creating for that. The issue when we do that is that if you have a single normal for each polygon, if we look back to the source code of what's happening here, if for a given 3 vertices in a triangle, if they all have, and we can't look at this example because of where it's being calculated, but if in our vertex shader, if we look at each vertices for a triangle having the same exact normal here, what is really going to be different? Well, the light position will be different because our input position will be different for the 3 vertices in our triangle, but it's not going to be a lot different, right? The vertices aren't usually that far away from each other, but the light position will be very slightly different. So the halfway vector will be very slightly different. But the end result of L.n and N.h, they are going to be different, but by a very small amount, if all of our normals are the same for the three vertices in our polygon. What winds up happening? Well, we've done all this calculation, we calculate our total color, and the ambient contribution would be the same as well, right? So exactly the same for each vertex in a triangle, very slightly different, and because of the power operation, very extremely slightly different for the specular highlight. The end result is a color for each three vertices in our triangle that's, if not exactly the same, extremely close to each other. That's why it's referred to as sort of flat shading, that even though we've done all these lighting calculations, you end up with a result that kind of sort of looks like the example there on the left. And that can also be still an issue even when we specify different normals for each vertex, but there's different ways we can do that. But if we don't even do that, if for each vertex in our polygon, because mathematically that kind of is logically consistent, we specify just a single normal, your bull's going to look something like this, this example over here, where it is lit, so it doesn't look totally flat like some of the earlier examples of the sphere with no lighting, but you can really see each triangle. One solution for that, and we looked at that for like the seal example there, is just to add lots and lots of polygons, right? So as you just increment or increase your polygon count, well, you don't really see the flatness anymore. It kind of looks pretty good. Ultimately, as your polygon gets as small as effectively what will be a single fragment or even sub-fragment polygons, a lot of those kind of edge cases kind of smooth themselves out and the result looks good. But that's very slow, right? We saw that with the seal model. After a certain amount of incrementing the amount of polygons there, the whole thing just kind of crashed. So it's very common to at least want to do, for Phong shading, have different normals at each individual vertex. And this is generally referred to as mesh shading, and we haven't had to worry about that ourselves because we either had a numerical model for what the normal should be, or we were doing things like loading our model from a mesh file, an object file that kind of took care of that for us. Either Blender took care of it for us, or some pre-loaded model took care of that for us. But if we ourselves are still in the business of having to calculate our normals for our particular object, then one such approach with what's referred to as garage shading is to just average the normals around a vertex to get the correct value for what that normal should be at that vertex. That would all have to be done on the host side, right? Because by the time we get to our vertex shader, we're only aware of one vertex in isolation. We don't have the knowledge of what our neighboring vertices, what their normals would be, but that would be one way to do it. You mathematically calculate for the plane equation what each of these individual normals should be, and now if you recognize that this vertex is not part of one plane, it is part of, if you're dealing with triangles, up to quite a few planes, but at least 3 planes here, then consequently, you can just average the normals for all those adjacent planes in your mesh and get at least something that's going to change. So for our 3 vertices in a triangle, again, whether that's mathematically correct definition of a normal anymore or not, you at least get a different value for n for each of the 3 vertices. That would lead to, without requiring lots and lots of additional polygons, now you'd have a different value for our color in the vertex shader as it kind of rasterizes itself away across the polygon for the actual color interpolation. That's still per vertex shading. The other approach, which is what that example that I had open in the separate editor here, is referred to as just full or proper Phong shading. So in the garage shading, we're still doing shading in the vertex stage, but we're having different normals, so we should get nice kind of interpolated looking colors as that end result. In Phong shading, and in the example we may have seen this now, we're not doing any shading at all in the vertex shader at that point. In fact, the vertex shader's role becomes pretty limited in terms of just doing the model view projection transformation still, figuring out where our vertices should be still, and then just passing the rest of that information along. Pass the normals along, pass the normals then to the rasterizer, where the rasterizer is going to be the one responsible for doing not exactly this calculation, but for determining not just now for each vertex what the normal should be, but for each fragment what the normal should be. And again, mathematically, what does it mean for a fragment to have a normal associated with it? I don't think you have to, have an intuition for that, but just recognizing that gives us a gradient of normals across our polygons. That allows for different normals on a per fragment basis. That should lead to then, maybe significantly different continuation gradient of color as we do our lighting calculation in the fragment shader itself. And that's what this example is doing. Again, in terms of the logic in this example, I would say versus the logic in this example here. I wish I had them in code side by side. Same number of calls to normalize, max, dot, pow. Again, it's code from different sources and it's written differently, but it's effectively the same what it's doing here. This one, in this example, we have to go back to the beginning to see this. This is definitely a vertex shader. The fragment shader for this corresponding example, at least for color contribution, would just be a pass-through shader again. It could be doing other stuff, but for color computation, for at least this part, it's done. Vertex shader did all the work. It calculated a color for my 3 vertices. Well, vertex shader and the rasterizer did all the work to determine what my color should be for my triangles in my object here. Whereas this example, even though in terms of lines of code, it's doing the exact same thing, is now, from the vertex shader's perspective, it's kind of, from the lighting calculation, it's kind of sort of a pass-through shader as well. It's moving the normal where it needs to go per vertex because we're doing the model view transformation here. So we're moving the normal alongside where the vertex is in the camera space. Otherwise, just passing that normal on through. And then the actual calculation is being done on on a per fragment post-rasterization. The rasterizer then treats the normal like any other attribute of my vertices as they're coming in, of my triangles as they're assembled together, and it just interpolates the normals like it interpolates positions and anything else that it may be interpolating. The end result, is something that's going to look a lot smoother than just the flat shaded or just the per vertex shaded model. And that's Gerard versus Fung shading. That's certainly the upside of doing it this way. What's the downside? It's going to take a lot longer, right? Now, it's hard to say how much longer, and we have to be careful being too specific here because it really is a function of your polygon density versus pixel density, right? But generally, I think we make the assumption that there's way fewer triangles than there are fragments in your scene. Doesn't have to be the case, and certain things kind of try to push the limits of that. But in general, we make that assumption. There's a lot of complicating things here, right? Once you add anti-aliasing, as the one team is doing, well, then you have that many more fragments as well. But you tend to want to have really small polygons already. But in general, I think it's okay to assume there's going to be more fragments by orders of magnitude than there are vertices in your scene. So the end result looks better, and the code looks really close to identical. But anything you run in your fragment shader is more expensive. I think orders of magnitude is the correct way to think about it than anything being run in your vertex shader. You may have seen this with MP3 to MP4. I think the easiest way to see that would have been just via the pass-through shaders where they weren't doing anything. But once you've implemented both the vertex and fragment shader hardware modules and you're just passing through a red triangle, it should have gone from, well, if it's just a single red triangle, you wouldn't really see it, right? But it should have gone from slow to order of magnitude slower, right, for the fragment shader. Because it's doing that same logic now. It's spending those cycles per fragment versus per vertex. So the same is true here. That's not to mean we certainly do that in practice, but that's kind of the downside of it, that every complexity you add to your fragment shader, there's the risk of an order of magnitude blow up of like the runtime, the computational complexity of your total render here. All I want to talk about lighting. Other questions, other lighting questions? Okay. Because there's limits to lighting. Lighting looks good for teapot and torus and sphere demos, and that's kind of all just pure lighting itself can do for you. And even though you can, render hundreds of millions at this point, more than that, polygons per second, it's going to be insufficient for all sorts of kind of real-world phenomena. There was a time when people thought like water was like the last thing we couldn't render properly, and there's lots of really cool techniques and whole forums at SIGGRAPH looking at rendering water properly. terrain was always considered to be a really difficult thing to render using just basic geometry. And there's companies who that's their entire intellectual property, that's their product, is rendering terrain really efficiently, giving you a really fast tree so you could render, tens of thousands of them as effectively as possible. Skin is something that we can talk a little bit about. Hair is still kind of something that is very difficult to model properly. But in general, there's limits to what you can do with a triangle. Yes, if I'm making a geometric shape, you can make it pretty perfectly with a triangle. When you're trying to model kind of real world phenomena, there's kind of a limitation of what you can do even with hundreds of millions of those polygons. And the example I give here is consider the problem of modeling an orange, kind of similar to our happy fun ball or our sphere, our globe example from the very beginning of this topic. If we were limited to just lighting calculations, and I'm talking about the actual piece of fruit, the orange, it wouldn't look very good, right? It would look like an orange kind of ball, right? One possible approach would be to recognize, well, an orange has lots of imperfections in it. It's not actually a sphere, and you can attempt to model it as a really complicated geometric object, and that is certainly a possible thing one can do, but there's just limits to doing that, and you've added a lot of complexity to your scene for modeling just a single orange. You may want a scene with two oranges. It probably takes too many polygons to model all the dimples if in the real world. In reality, we are not made up of triangles, and so modeling reality with triangles has limits, even with the advantage of what lighting allows us to do to make things look more three-dimensional. And that's the very high-level motivation for why we do texture mapping in the first place. It's a more practical approach, just like our lighting calculations are, as we said, a hack on top of an approximation on top of an approximation. Arguably, texture mapping is as well. In texture mapping, we're basically faking the fact or hiding the fact we have a very low frequency information of triangles trying to generate this orange, trying to reflect what an orange would look like, and we're papering over it with some pre-calculated high frequency texture, some image that has been pre-calculated, pre-generated for us. And that is basically what we're doing. Texture mapping is the process of mapping an image, oftentimes a 2D image. I think we can stick with 2D texture mapping without losing too much generality here, just in order to increase the amount of detail in the resulting rendering. So if we had a geometric object here, this is from the great Ed Angel textbook, where there is some detail. So it's not just a sphere, but there's not a ton of detail. I mean, you can see that if this is all geometric, there's a decent amount of detail. We have a shaded object here. We can then add that significant additional detail to it without changing the geometry at all. So in this example, this is the same model that's being rendered. The only difference between these three resulting renders is the texture that's getting mapped to those three examples. And there's a lot of variance in that as well. This is meant to be an example of what's referred to as reflection or environmental mapping. The idea being, we already have this concept of the camera in the scene. That's what the scene looks like from the camera's perspective. There's nothing preventing you to rendering that to a texture. So you first render the entire scene to a texture. You then apply that texture to the resulting object, and you get kind of a mirror-like looking object where you can see what does the world look like from that object's perspective. There's also bump mapping, and we're going to get a very nice tutorial in bump mapping at the end of this semester with your team. I was going to tell me all about how we can change the normals to get those really small perturbations of what the lighting should look like to get a nice looking orange at the end of the day. There's different ways of doing bump mapping, but that's the approach that I believe your team is going to be taking for that. I like this demo. It's actually kind of old now, but I think it gives a good example of, even with a really detailed model of a hippo, when you're just using shading techniques, there's just a limit to how much realism you can get back out. This is a pretty high detailed mesh model here. This is not just a few triangles making up a sphere any longer. And you can tell it is what it is. It looks decent with what it is, but the amount of realism one can get visually by just applying textures to those even highly detailed models shows what can be gained via texture mapping versus just trying to get more realism being via increasingly detailed geometric models here. In general, when we're talking about texture mapping, we just have to determine for a particular texture, again, just think if that is the image to be applied, we just have to determine where in the resulting model should the corresponding region of that texture be applied. I like to think of it as the wrapping paper approach because it's kind of what it is. You have this image, this is the wrapping paper. You have the model, this is the object you want to wrap the wrapping paper around. And you are determining and you're specifying via your OpenGL code where in the wrapping paper should this be covering that particular object that you want to wrap. Again, for geometric objects, you can have a mathematical model for that. We'll go through a very quick example of that. For real-world objects, you can't. So, for example, we have to kind of do both the texture generation and the modeling of the object hand in hand to determine not only are we determining what the vertices should be for the mesh corresponding to this object, we have to then determine what the normals should be for those corresponding vertices in our object. We then also have to simultaneously determine what should the texture coordinates be for the corresponding texture we want to map to that object. So it's really not one and then the other. For anything that can't be just mathematically specified, they're one and the same. It's all part now of the modeling process where you're specifying not just position, not just normals. You're also now, instead of specifying color, you're specifying texture coordinates, and you're going to combine both the lighting calculations with the texture mapping calculations and process associated with it to get your nice lit, realistic looking hippo back out. So I should mention something just as a gotcha for the two teams that are doing texture mapping. All the examples you will see in any of the tutorials, the how-tos and whatnot for how to do texture mapping, take awesome.jpg or take images and work with images. There's a real risk for you in working with images until you have other stuff working. The risk is that there are many variants of what OpenGL as a language API can support for texture mapping. Hundreds to, I don't know, let's just say hundreds of variants of what will work with OpenGL. Your hardware is very likely you're only going to want to support one variant, right? Limited to like one thing that you're supporting properly. Once you're dealing with images and image formats and different resolutions of images, each one of those adds an extra variable to your implementation. And you can get really frustrated because it may all look really good in OpenGL because OpenGL should be able to handle all these different variants. It's actually doing some kind of edge case stuff for you that you don't even necessarily even see underneath the hood, but then in hardware it's going to be not what you're expecting. Definitely start with just manually created textures, start with a checkerboard pattern. Just start with something, mathematical that you can understand. At location 47, it should be black, this texel, because I created it in my code, versus worrying about why does the beard look wrong in this location. I mean, that's a different issue entirely. Because that's going to be extremely hard to debug, and it's going to be very hard, I think, to be frank, for you to know whether it's an OpenGL issue, whether it's your driver issue, or whether it's your hardware issue. And just like going from 0 to 1 for like a single pixel, took some time. 0 to 1 for a single texel is going to take some time, and you should start with a texture map that, all white I think has its issues too, because maybe you'll fool yourself into thinking it's working, but a simple checkerboard white and black texture map is definitely the way to start. And then once you get that working, then do awesome.jpg. So at a high level, this is what's happening with texture mapping. And again, we use images for all these examples because they look more motivating and makes more sense to use real images in real applications. But as we are specifying our positions for our geometry, we're also potentially specifying normals. So I'm not showing that here, but we're also potentially specifying our normals. We're also going to be specifying our texture coordinates. And this is for a 2D texture, so 2D texture coordinates. Depending on what references and resources you're looking at, the texture coordinates will have different attribute names for your swizzle operator. .u, .v is very common. .strq is another version you'll see here. These slides use UV, but a lot of other resources use .s and .t. OpenGL supports all those component selections, so it'll work. You could do .r and .g as we've talked about, right? You just need the first component and the second component. It's not exactly X and Y because while this is a two-dimensional image here, we're not really thinking of it in a positional way. We're thinking of just parameter 1 and parameter 2 of our texture map here. But that is what you are specifying. With 0, 0, I'm not entirely sure if that's correct, but for this example, with 0, 0 being the upper left texel, for 1, 1 being the lower right texel, you would specify then some value between 0 and 1. As you're specifying your positional attributes, you're then also specifying your texture coordinates corresponding to that. So if this was a quad that we were rendering here as part of a cube, and it's a little subtle, but V1 is here, then we specify V2, V0, V3, so some sort of triangle strip here to specify our quad. Those are our positions. So that's V1X, V1Y, V1Z, same for V2, same for V0, same for V3. In addition to doing so, we're also specifying, just as a separate attribute, separate buffer object, we're specifying our texture coordinates. So we'd want to potentially specify for V1, give me texture coordinate 1, 0. V2, give me 1, 1. For V0, give me 0, 0. And for V3, give me 0, 1. We'll talk about the mechanism by which this happens. The long and short of it is we pass that as a vertex attribute. Vertex shader just kind of passes those on generally. Rasterizer then rasterizes those attributes like it does every other attribute. So we specified this one as 1, 0. We specified this one as 1, 1. And we get a gradient in that V dimension as we rasterize down that line, right? So this would be 1, 0.5 right around here for our texture coordinate. There's going to be issues because we have a discrete image here and we have kind of a continuous UV space here. But in general, that's what we do here. We're sampling from the image based on those coordinates. So when we do that mapping, we wind up with something like this. You can see where Jeremy got the idea for the Zambrino cube. It was not, in fact, his idea. And how we dictate that, those UV coordinates, then tells us how that mapping is going to happen with a lot of supported variants of that texture mapping. This is, I think, the only reason this kind of gets complicated from a hardware design perspective for us is that the parameter space is really, really large, and we just have to pick, a feasible, implementable subset of what we want to support. But it should be able to handle all sorts of different images. So here's other.jpg. If, for instance, we now are specifying our top rectangle here of our cube, our top quad here, so that's V7, V8, V1, V0. And for UV, we're actually specifying 0, 0 to start with, so that's fine. That's our upper left. Then for V8, we're specifying 4, 0, 4, 3, and 0, 3. I don't expect you to necessarily know this. What do we think is going to happen? The answer is it depends on some other parameters, but in general, what will happen for this? Could be. But this is all PowerPoint rendering. This is not actually as rendered, but you'd get something very similar looking. A couple things could happen. It could either stretch. It could tile. It could also, I think the term is flush. It could just take the last value and just kind of flush it all in all dimensions. So whatever happens to be the last texel in each of these dimensions would just kind of get stretched out to the end, but the inner part would look fine. I think by default it would do tiling. So if you specify 0, 4, it's actually going to give you a multi-Jones cube. So for any of the teams doing texture mapping, that's my only request. You don't need to do a Zambrino cube. It's already been done. That doesn't count as an original project. Jones cubes are very much allowed, so you have my permission to use this or any Jones image you can find for Jones cube texture mapping. I was kind of getting to this point here, but so textures can be one-dimensional, two-dimensional, three-dimensional. There's general dimensionality you're supporting. I think in terms of visualizing what we're doing here, while our geometry still stays 3D now at this point in the semester, keeping our textures to 2 dimensions, I think, is the right way to kind of limit our perspective, and we're not losing that much generality. So in a 2D texture, we have a separate parameterized coordinate system. I would kind of prefer it be like something like T sub X and T sub Y, and you do see that in some places. Textbooks versus implementation, you'll see those coordinates as UV or ST. Those are the same exact thing. That's just parameter 1 and parameter 2 of a 2D texture. Generally, width dimension and height dimension for that texture. So if you think of it in those terms, I think you're going to be okay. Lower left, yeah, that example wasn't quite correct. So in OpenGL, lower left, the image is coordinate 0, 0, and the upper right is coordinate 1, 1. We've talked about that a few times, right? About the right-hand rule for what is positive Z, for where upper left in our screen spaces versus our normalized device coordinates. And I never get too like stressed out about those. Did I get upper left correct, or was it supposed to be lower left? Ultimately, if you get it wrong, I always feel like it's a very fixable, because it's one of two possibilities, right? It's either upper left or it's lower left, or at worst, it's four possibilities. And you get it wrong, you do it wrong, I told you wrong, and the slide had a bug in it, you can blame me, but then you should have a flipped up, the texture is just gonna be flipped upside down. So that's a very fixable thing, right? When you got the exact parameter wrong and you got the thing exactly the wrong way. The limits are not that textures are going to be a power of 2, but the resulting hardware is quite a bit simpler if you assume your texture sizes are of a power of 2 in each of the dimensions. That's not an OpenGL limitation. I'd like for teams doing texture mapping to have that as their own self-limitation. Just for the address and sampling calculations you're doing, they're a lot easier if everything is going to be a power of 2. And what we'll talk about starting on Thursday is there's a little bit of kind of sampling a theory associated with this, right? Very few of us are double E's in this room, but understanding that we are going to have this image that is of a particular resolution. And if it's not something that's computationally generated and it's actually based on some real world image, there's some actual pixels associated with that, which are referred to as texels when we're doing this texture mapping here. And we're going to be mapping that to ultimately something in screen space in our fragment shader, where we're determining, given a texture coordinate of UV, and for 0, 0, and 1, 1, it's okay, but it's for all those values in between 0 and 1 where we're interpolating those values via some, in our case, fixed point implementation of a floating point value between 0 and 1. So we're sampling from this image. So the real challenge in texture mapping is how do we do that, both that it's correct from a perspective way of looking at things. If there was a perspective view on this cube, understanding what those texture coordinates should be in reality requires a little bit of additional thought. And then just in terms of, given a value of UV between 0 and 1 now, some arbitrary fixed point or floating point value between 0 and 1, how do we determine which value from that relatively large texture we actually want to grab, and how do we make sure that we're actually sampling at a reasonably correct frequency so that the texture doesn't wind up looking very strained, stretched, or even when we're minifying shrinking the texture, does it actually still look good based on what we're sampling from the texture at that point? Let's leave things here with the Jones cube, just to give you that final inspiration. We'll talk about more on Thursday about what this means in practice, with some demos like anything else. But I think there's no shortcut to kind of experiencing it yourself. But as you're starting in projects, some of you have definitely already started, which is wonderful. As you're really starting in earnest on Wednesday, that general philosophy of let's minimize as many variables as possible with our implementation, knowing that maybe it's not exactly what we want at the end, but we can always add as we keep going, versus let's get our final demo working, because the steps along the way, the frustration you'll feel will be much worse, I think, in that latter approach. That's just my opinion. But similarly, work backwards from what you'd like to demo. And you should be writing as your team, one member of your team, maybe the team splits it up. Lots of OpenGL applications along the way, right? Lots of different shaders, lots of different demo things to be able to show, here's what we want at the end of the day. Here are the steps that we need to show are working to get to that point. And having lots of demo applications or test applications, whatever you want to call them, is going to allow you to do that. So while the temptation to get the Jones cube working on Wednesday is great, I understand that. Start really small. Checkerboard pattern is the way to go. Then worry about other uses of texture mapping, other things you can do to get more advanced features working as we continue to cover that in class. Let's leave things here for today, and I'll see everyone on Thursday.